3, 2, 1.
Hello. Okay. Yes. Welcome to Korosi Indonesia podcast. I'm Febriana Putita Sariwaluyo, together with my host and co-host Richard Dasari and Sina Sulaiman. In this podcast, we will talk about microbial induced corrosion, or MIC. MIC is broadly defined as corrosion affected by the presence or activity or both of microorganisms, including bacteria that form biofouling, field degradation, and under-deposit corrosion. While microorganisms and biofilms are ubiquitous in nature, not all corrosion is microbiologically influenced. Determining the degree of corrosion mechanisms and vice versa is the essence of diagnosing the likelihood of MIC in a particular environment. In defining the potential for microbial influence, certain environmental conditions such as temperature, salinity, oxygen content, sulfate and nitrate availability, organic carbon, and pH in the system and potentially contribute to MIC. Understanding these conditions in an asset is critical to determine the MIC likelihood. And today, we're going to explore more about microbial induced corrosion or MIC with our special guests, the two experts of MIC. First, Dr. Reza Javaherdashti, the CEO of MICORR. He is being involved in more than 400 corrosion management projects worldwide, approved by ASME and SP as corrosion MIC. Lecturer with more than 5 hours of experience in designing and delivering successful training courses. Author several research papers, root cause analysis reports, and 8 books. And our second special guest is Dr. Martin Choirul Fatah PhD from Oceaneering at Integrity Jakarta. He has more than 9 years of working experience with a good track record of technical engagement and performance, being involved in several corrosion management projects and authored several research papers. Okay, Pak Richard and Pak Sina, time is yours.
Thank you. Thank you, Fabiana, for a good introduction. Dr. Reza and Dr. Martin, maybe I just call both of you like that. Thank you. Welcome to NACE Indonesian Corrosion Podcast. So other than names and little bit brief introduction that already Fabiana mentioned, maybe you want to tell more about yourself, your education, your work, and your experience. Maybe start from Dr. Reza and then go to Dr. Martin. Thanks.
Thank you very much. I appreciate both you and your colleagues in organizing this podcast regarding microbial corrosion. Yeah, I have dedicated more than two decades of my life into research and also troubleshooting issues in various industries around the world, including in Indonesia. I had a microbial corrosion workshop some years ago. I have worked in many industries, oil and gas, power generation, many industries worldwide. I have also authored several root cause analysis reports as well as research reports. I am the author of 8 books on the subject, published by publishers such as Elsevier, Wiley, Springer, And at the moment, I am the CEO of my company in the Netherlands, MICORR. And here we are dealing with corrosion management in general and microbial corrosion in particular. The recent project that I finalized, it was for Shell regarding modeling of microbial corrosion. Regarding microbial corrosion in particular and corrosion in general, most of the time when my colleagues want to address it, how to treat microbial corrosion, they normally talk about measures such as use of biocides, coatings, etc., which are of course very important. However, in my opinion, one of the most important points is to find a way to predict the likelihood and risk of microbial corrosion. I will, as we proceed, I will talk about the difference between likelihood and risk, because it is an issue that most of the time is overlooked. Some people, I have seen many managers and even professionals who mistake likelihood of microbial corrosion with the risk of microbial corrosion. The thing is that when it comes to microbial corrosion, if you don't mind, I want to just go further, and in addition to a short introduction about myself, start the discussion by just adding 2 points very briefly, and then I will hand it over to my colleague, Dr. Martin. One thing is that there is a vast difference between corrosion and degradation. Corrosion is only applicable to metals, whereas degradation is applicable to non-metals. And when it comes to the role that is played by bacteria, for example, MIC basically describes corrosion enhanced, initiated, or even sometimes stopped by bacteria on metals. But when, for example, you want to talk about so-called microbial corrosion of concrete, it is appropriate to address it as microbially induced degradation, because concrete itself, the cementitious material, is not metallic, and therefore attributing the terminology corrosion to it is not correct unless you address microbial corrosion of the steel reinforced bar inside that. So this is very important, and most of the time it's being mixed up. MIC and MID are different because the materials are different. This is point number one. Point number two is that, as I just mentioned, contrary to what we may think, not all the time bacteria enhance corrosion. Under certain circumstances, although you could have bacteria around, they may not be doing any harm to your system. Therefore, just having bacteria in your system does not necessarily mean that your system is in the risk of MIC. We will hopefully describe this in more details as we proceed. Thank you.
Yes, yes. Very interesting, Dr. Reza.
Yeah. Dr. Martin, over to you.
Okay, thank you, Pak Richard, Pak Sina, and Bu Febriana, and Dr. Reza. Nice to meet you. Finally, I can meet you directly. I know your name since my study about maybe 15 years ago. I read your book and referred many of your papers to my study. So it is, I'm glad to be here to be with you to share the knowledge about MIC. Okay, my name is Martin. I finished my PhD in corrosion. At that time, basically, I want to study about the MIC, but unfortunately, the lab is still the development, so that I'm using abiotic chemicals to simulate the effect of MIC. After finishing my study, I continue to work in the EPC. Mostly my job is related to RBI and corrosion. That's all from my side. Thank you.
Thank you for you both. Pasina, over to you.
Okay. Okay. I think, Dr. Reza, I think we can continue on your explanation about the MIC because our audience is various. I think we could have like the undergraduate student which may not know exactly what is the MIC. So maybe could you help us to give a brief
Sure,
explanation what
sure.
is the MIC? And then to be honest, I'm interested with your statement before about the MID degradation, which I think we haven't considered it yet, right, Parichat?
Yeah,
We may consider it as a general MIC, so that's very good.
yes. Okay, okay. Thank you very much. In order to understand MIC, one has to understand corrosion or what is meant by electrochemical corrosion. Let me take you back with me in time and tell you that whatever metals you see, engineering metals, like, for example, various types of steels, copper, alloys, etc., etc., they are basically coming from their ores. And these metals in their ores are in their minimum state of energy. That's why no metals basically can kind of, come out of ores, its ores automatically. You have to crush the ore, the stone, and basically apply extractive metallurgy to extract the metal out of its ore. During extractive metallurgy processes, what you do is basically you inject electrons into these metals. These extra electrons are like unwanted guests because they are not coming from the material itself. We are pushing them on the metal. These unwanted guests, these extra electrons that we apply during extractive metallurgy processes, are always in a restless condition. They want to get rid of where they have been put into, so they want to escape.
Yeah.
This natural tendency for these electrons to basically get rid of their present condition is what we call as corrosion. In other words, these electrons want to kind of get liberated from the metal, and when these electrons are coming off the metal, and then they are being absorbed somewhere else, an electrical current is being created. This electrical current can be measured, and this is what we call as corrosion rate, or how fast corrosion can proceed. Therefore, there is a relationship between the transform of these electrons from from spots we call as anode to cathodes, where these electrons are being observed, and that how intensive or how fast corrosion can proceed. When you have factors that can facilitate, that can assist this electron travel, let's say, it means that corrosion becomes faster. One of these factors is the action of bacteria. Why? Because bacteria, like we human beings, they need energy. And in order to produce energy for themselves, they need to have electron transfer so that they will be able to transfer food into energy for themselves. These electrons that are being used by certain bacteria happen to basically assist corrosion, and what we see is then called as microbial corrosion. Simply put, when bacteria use the electrons that are thermodynamically being liberated, being freed from metal, when bacteria use these electrons for their metabolism, they contribute to corrosion, and it is the reason that they contribute to corrosion, and we see it as very high corrosion rates. Like, for example, in case of sulfate reducing bacteria, the notorious SRB, you could achieve corrosion rates up to 36 mpy. Mind you, when the corrosion rates is above 5 mpy, it is said that corrosion conditions in your system is very, very severe and very enhanced. Just imagine, instead of getting 5 mpy, you get something like 36 mpy. That's why when you have some bacteria, these bacteria, under certain circumstances, they can actually increase the rate of corrosion. Therefore, if for example, in Australia, the life of structures, basically flow lines that are designed for having a life of at least 5 years, could be reduced to 2 years, maximum 3 years, because of the action of bacteria such as SRB. And the reason that we do not like MIC is the damage they basically force us to withstand with regards to losing a lot, money, and of course, waste of energy. Let me give you an example regarding how important corrosion is. International figures shows that every 90 seconds, 90, every 90 seconds, 1 ton of steel corrodes. And the energy that is being used in order to produce 1 ton of steel is roughly equivalent to the energy that a medium-sized family can consume over 3 months. That's how important corrosion is. And anything contributing to corrosion, either bacteria or else, is very important and must be taken care of seriously. Regarding MID, microbiologically induced deterioration, bacteria can also affect nonmetals. There is one of the myths that some experts even have is that, for example, polymers and composites are immune to microbial degradation. This is not true. We know that plastics such as HDPE or even epoxy could be used by bacteria as food. Therefore, I would say no engineering material is immune to corrosion and microbial corrosion particularly, especially non-metals such as composites or concrete, and this is also a very important aspect of microbial corrosion and MIC and MID that must be taken care of. Thank you.
Okay. Thank you, Dr. Reza. This is really comprehensive explanation. I think question for you, Dr. Martin. How many MIC characterization techniques available that we know? What are the common technique used by the industry at the moment? Where this technique can be implemented and what are being analyzed? And also the last one, what are the limitation? Thanks.
Okay, Fadishat, I will try to answer that question. As far I know, MIC is the results of the confluence of 3M, which is microorganisms or microbiology, and then media. Media is in this thing is that there are chemical composition, physical parameters such as temperature and flow, and also metals or metallurgy. So to characterize the MIC in the system, we should consider these 3M. But for the microorganism, we can diagnose the MIC. First, we are using the bacterial identification and quantification. But there are some important note. The first one, the metallographic features and treat morphologies cannot be used to diagnose MIC because we found that the tuberculous and hemispherical pits in 300 series of stainless steel localized at wells and channeling in carbon steel are consistent with some mechanisms of MIC, but cannot be interpreted as MIC. The second one, the planktonid cannot be used to estimate the numbers and types of microorganisms causing corrosion. And then the planktonid also do not indicate the quantity or location of microorganisms within the biofilm. And then the numbers of cells and MIC kinetics cannot be correlated regardless of the quantification method. So as the conclusion, the microbial quantification can only indicate the extent of the microbial presence, but not to predict or diagnose MIC. And then for the detailed information regarding sample collection, storage, and examination techniques for MIC, advantages and disadvantages, and their limitation, I suggest to refer to the papers written by Videla, B.J. Little, H.C. Fleming, and etc. Because this is very biological related and maybe quite difficult, especially for me to understanding that things better. The second one is the Aminological method. So this one is to check the corrosion product because the bacteria creating the microenvironment below the biofilms, and it will resulting the different environment with the bulk solution in terms of temperature, pH, pressure, disoxygen, as well as the concentration and type of organic and inorganic species. As the consequence, the corrosion product resulting from biomineralization can be different from those produced in abiotic environment. And then we also can use the chemical methods. So it is helpful to determine if the microorganisms are present at the corroded site. The very simple qualitative test is to scratch some of the material from the surface. For example, with a knife, then we heat it with lighter, and then if we smell the hair or the meat burn, this one indicate the presence of protein or refers to biological material. But the most sophisticated and commercially available protein tests are recommended to be used. I think that's all, Pak Richard, from my understanding about the MIC detection.
Yeah, thank you, Pak Martin. I think from my point as a practitioner, I think it's really important to understand what is the techniques and also the limitation that you already mentioned, because many times we fail to understand the result because we fail to understand the limitation. Just based on my experience. Okay, go over to you, Pa Sina, for the next questions.
Before you,
Go ahead, Dr. Reza.
Sorry, before we start, I would like to add just two more points.
Yes.
Currently, one of the mostly referenced standards about MIC is the so-called TM0194. This standard suffers from many defects, and with a group of our colleagues, we are planning to hopefully rewrite it again. Although the standard contains a lot of useful material for detection, monitoring, and even kind of classification of methods regarding MIC detection and classification, as I said, it still has some disadvantages. There is one point that pertains to MIC literature, and it is the word biofilm. Biofilm is wrong. It is a terminology that was coined in late 70s, I think 1978 or something. And the term itself implies that you will be facing with a film which is 100% biological. Neither is true. Biofilm is not a film. It has a patchy nature, and just about 3% of its dry weight is biological. The rest is non-biological. That's why in the year 2020, I published a paper and I suggested that instead of biofilm, which is a wrong term to address a right procedure, it's better to use another term that I called as temenos. It comes from, it's a Greek name. It literally means cut off. And the reason I suggested this term is that when you have so-called biofilm formed under biofilm conditions could be vastly different from conditions outside the biofilm. For example, outside of the biofilm, you could have oxygenated conditions, whereas under the biofilm, you could have anaerobic conditions. Outside the so-called biofilm, you could have neutral pH values. Under the biofilm, you could have very low pH values. So I would like to use this opportunity to once again announce that the term biofilm is not correct, and this can cause a lot of confusion even among professionals, because they think that they will be looking at a film that contains antibiological matter. This is not correct, and this is also very important because if we can differentiate between the concept of a film and the concept that it is not a 100% biological matter, this can also affect the way we look at corrosion cases. In my publications and classes, I always advise that when you have a case of corrosion and you think that it could be MIC, first try to explain it in terms of not involving bacteria. Try to explain it in terms of non-MIC terms. And only when you fail, then try to involve bacteria. Because if you do it the other way around, then it is highly likely that you make a mistake and you may even make the conditions worse. Sorry for the interruption.
Yes.
Thank you, Dr. Reza. I think that's really good. Over to you, Pak Zina.
Yeah, that's very philosophical approach. Yeah. I think that's the correct way to understand the issue. I think we are going back again to your previous statement, Dr. Reza, about the about the probability and then also the risk. I think one part of the task for the corrosion engineer is like to do the threat assessment of the MIC in the system. So maybe you could provide us like the advice, where should the corrosion engineer start if she or he wants to do the MIC threat assessment or the mapping in the facility. So maybe you could go back again. What is the difference between the probability and the risk first, and then
Yes. The risk is actually a function of likelihood and consequences. This means that although the likelihood of having a certain danger, like for example microbial corrosion, may seem low, because of very high consequences it could have, therefore its risk could be critical. This is to address the confusion that sometimes, especially in industry, you may face. You can see people who say that we are already using biocides, we are already using CRA, corrosion resistant materials, we are already using cathodic protection, coating, blah, blah, blah. So the possibility of microbial corrosion must not be high. This means that in their opinion, the likelihood of MIC is rare or very low. However, they do not consider that if MIC happens, because of the consequences it can have, either from the damage it can have on environment or from the financial point of view, the product of likelihood and consequence would make the risk very high. So if you have somewhere stagnant water in liquid form, in contact with rough surfaces, particularly surfaces after practices such as welding, on which post-weld treatment has not been carried out or has not been carried out completely, this could be one of the points in which the likelihood or risk of MIC could be high. If, for example, you have practices such as hydrostatic testing, normally when you have hydrostatic testing in pipelines, as you know it much better than I do, more than 95, 98% of the pipelines used in oil and gas industries are basically welded pipelines. Yep. And when the operation pressures are above 60 psi, in order to basically test both leakage and strength, hydrostatic testing is used. Hydrostatic testing is different from pneumatic testing. In pneumatic testing, you use gas, for example, in order to just measure the leakage. When you want to measure both leakage and strength of the weld, you apply hydrotest. Most of the time, the water that is being used for hydrotest comes from sources like seawater. The water must be taken from a certain layer of seawater. You cannot take it from any depth you want. It must be taken from a certain layer to decrease the likelihood of MIC. And if, for example, you apply a hydrostatic testing and then go for example, wet layup with the same water, then you increase the risk of leakage due to use of hydrostatic testing and microbial corrosion. Basically, let me give you this. If you have water into and you put it into a pipe, okay, and the dissolved oxygen in this water is at the level of parts per million, after 24 to 48 hours, because the oxygen is being diffused out of the water, the amount of oxygen, the amount of dissolved oxygen from parts per million, ppm, drops to parts per billion, ppb. This means that your system would become anaerobic anyway. Yep. And if in the water you have used, you don't apply, chemical treatment such as use of biocide, corrosion inhibitor cocktails, etc., then microbial corrosion could be a very strong possibility. I have seen many of these cases that I have gathered in my book on hydrostatic testing. Also, if, for example, the pH bacteria can live in a very wide range of pH. It could be from 2 to even 7, 8. Like for example, we have sulfur oxidizing bacteria that can produce sulfuric acid with pH 2. And I was once working in a facility that were using these bacteria for bioleaching of copper compounds, or better to say copper ores, you know. So the pH is important. The corrosion potential is important. For those of us who may remember their undergraduate courses from Purbe diagrams, you would remember that these Purbe diagrams are constructed based on pH and corrosion potential. Okay, in industry, when an engineer sees that the pH, for example, is 7, he automatically assumes that the conditions are not corrosive. However, if you go back to Purbe diagram, you see that even at pH 7, if corrosion potentials around certain level, the environment could be corrosive. If pH is 2, however, the corrosion potential is around certain level, your system could not be corrosive at all. So just by looking at pH, you cannot tell a story about your system. Another issue is that when you are considering microbial corrosion, you must differentiate between the so-called planktonic bacteria and sessile bacteria. What I mean is that bacteria in their normal state, they are planktonic. They are freely swimming in the bulk water, okay? And if they cannot find food in the bulk water, and this food goes down and precipitates in a sense or sits on surfaces, then bacteria from this planktonic state go and become motionless. This is a very sophisticated, complex procedure, but it is important because when bacteria change their status from being planktonic to sessile, it is not just a simple change of status. Their genetics also change. Therefore, when bacteria become sessile and motionless on surfaces, with very small amounts of food, they can unbelievably high rates of metabolism. That's why about 90% of corrosion comes from the so-called motionless sessile bacteria, otherwise known as biofilm, and 10% from something around 10% from planktonic bacteria. So if my engineer goes and takes a sample or sends to a laboratory and then comes back to me and says, Reza, the number of bacteria, for example, SRB, shown here is, for example, 10,000 cells per milliliter, I will say that this is of no use to me, because this shows the amount of your bacteria in planktonic states. Don't forget, it says cells per milliliter. Then it means that they have measured the volume. Go back and bring me results like the amount of SRB is, for example, 1,000 cells per centimeter square. This means that they have measured sessile bacteria on the surface. And this is the type of information that could be much, much helpful to you than just what we normally do with culture related methods, such as serial dilution, etc., etc. Thank you.
Just at that point, Dr. Reza, as an owner of the facility, the sampling position is not always on the tank floor if we talk it about a tank farm. And that's really difficult to get the sample from the tank floor, because usually sampling point, they have a gap. So is there any advice for that? Because I just admit that we have been doing like the other one that we measure, because that's the possible way to do, and it's pragmatic as a facility owner.
That
This is, yeah,
purchase
this is a
order.
Yes,
very,
go ahead.
yeah, this is a very important question.
Yeah.
And I understand your concern. Yes, you're right. It is very important. It is very difficult, actually, to get sessile samples from the bottom of the tank. One thing that in my practices I have used, when let me just make a little joke. Like, for example, every cook has his own tricks. Okay, if I mean, my mother can make the same food as your mother, but your mother's food would taste much different. It is not the food, it is the tricks they use. This is one of the tricks that I normally use. I go for severe agitation of the liquid in the tank. Like, for example, you have a propeller and you agitate it very severely, so that even if there are biofilms or temenos formed, there will be a possibility for them to just be taken off and come into the bulk. And as soon as the agitation is over, you start to take your samples. And then these samples, when you take it, you just allow for some time for the bacteria just to settle. This is the only way that may come to mind, which could be practical under field conditions. When it comes to laboratory conditions, life is easy. You can always, find a way. But when you are talking about a 3 million liter, about a tank with a 3 million liter capacity, it's not a joke. So one thing was this, that you apply a lot of agitation so that there could be a chance for taking samples. The same is also true with fire water lines. I have been engaged in several such projects, because when you have fire water lines, underground fire water lines, water sits there for long times, and it is always possible that, like the way that it happened with hydrostatic tested pipes, okay, it is possible that this water will start to be leaked out because of microbial corrosion. I have seen several cases of that. So what we do is that we do the same. We start to play with pumps and do some sort of severe agitation. And after running it for 1 hour or so under very severe agitation regime, then we stop it and start to take samples from several sampling points. And this can actually give you a very good sort of result, as I said, based on field conditions. This is what I have experienced.
Okay. Thank you, Dr. Reza, for the explanation. I think it is challenge when you working with the 200 or 300 barrels capacity of the farm
Yes,
tank.
yes,
I think
yes.
another things that we can do as well. We can just turn on the circulating pump. Usually we have 2 or 3 circulating pump to just
Yeah,
mix the product,
yes,
and
yes,
that is another things that I'm thinking about.
yes,
Yes, no wonder. So for the past 7 years, we have sporadic reading of the SRB, the because we took the sample when there is no loading,
yeah,
the no condensate loading, where I think it should be the other way, right? So when we
Yeah.
when we have the condensate loading, when we circulate everything with the
Yeah.
pump and it's sporadic flow, that's
Yes, yes,
the
yes.
good opportunity to take the SRB samples and I think to get real data from the SRB rating.
And don't forget that most of the time people don't see any case of microbial corrosion because they do not see SRB. Mind you that it could be well because you could have, for example, Clostridia in your system. These guys are also anaerobic and they are similar to SRB, but with normal kits that we have, they are not being measured. So they see no SRB, they assume no MIC. They see no sulfate in the chemistry of their system, they assume that there is no SRB then. However, we do know that you could have no sulfate in your system, still you could get sulfur-reducing bacteria. And this is very important issue. Hopefully, maybe in the future, we will be able to talk about this and similar issues in more details.
Okay, thanks, Dr. Reza. I think that's my turn as well. And this is question go to you as well, Dr. Reza. So, as a owner facility or usually people who have the facility or if you have any facility, it is very important from management to say how many SRB we have. Is that a risk? Should I worry about that? Or do you think it can withstand for a couple many years? In order to do that, we have to establish, like a KPI, right, or a
Mhm,
mitigation plan or
mhm,
monitoring plan.
mhm. Yeah,
Otherwise, it's just difficult
yeah.
to
Yes,
quantify the bacteria that we have.
yes,
So the
yes.
question is, what is the effective barrier to mitigate the threat of MIC?
Mhm,
Or and then another next following question from that: what is adequate monitoring, measurement, or KPI that somebody can put, which is pragmatic,
mhm. Yeah,
to the point, and really easy to understand, and also
yes,
really easy to replicate to another facility if we
yes,
see the threat in
yes,
this
yes,
point. We
yes,
can just do it very
yes,
easy in another spot. Yeah,
yes.
thanks.
My colleague, Dr. Martin, already said that basically there is no relationship between the number of SRB and corrosion rates. That is true. However, in my publications, in at least two of my books, I have given something like a KPI table that is being used by some companies, oil and gas companies around the world, in order to have some idea about the so-called safe number of SRB, safe number of general aerobic bacteria, safe number of general anaerobic bacteria. I can share the names of those books with you later, and you may communicate it with your colleagues later. If I was a scientist, unfortunately I am, I wouldn't say that there is any practical way to ensure your manager that his facility is not in danger or is in danger of microbial corrosion. But as an engineer, unfortunately, I am an engineer too. I would say that there are some um, uh, tables or KPIs that you can use in your communication with your managers. These KPIs must be used very carefully, and I have always advised that in corrosion in general, and in microbial corrosion in particular, the most important issue is not recognition of the case as being microbial corrosion or even its treatment. The most important issue is monitoring. You have to always monitor. And I have always likened it to having an old sick mother at home. You know, you always have to call her. You always have to be careful what she's doing. Is she doing right? And your system is just like that. Especially when you have microbial corrosion or risk, likelihood of microbial corrosion in your system, you must be very careful. Monitoring is the key. There are methods for monitoring available, commercial kits, coupons, or even devices such as BioGeorge, for example. There are, if you do a small, Google search, you can find a lot of them. Whatever you do is to take care of 3 points. First, do your corrosion management homework well. What does it mean? It means that if you have right material in place, if you have done coating, good coating with high adhesion in place, if you have done cathodic protection in place, if you have done your homework well, having bacteria in the system does not necessarily mean that you have to be panicked about microbial corrosion. So doing your corrosion management homework well is important. 2, have a monitoring system installed in place. For example, linear polarization devices or whatever that shows what's going on in the system from even an electrochemical point of view. Add to it coupons that can give you a collection of biofilms, temenos, and how it affects, like, for example, the BioGeorge. All these, of course, they have their pros and cons, okay? But if you are aware of the number of, for example, if you do regular tests regarding the number of planktonic bacteria in your system, which is much, much easier, this can help. I have given in my book on failure FMEA of microbial corrosion some algorithms that can be used for fire water rings, and by applying those algorithms you can be sure that up to a good level of reliance you are on top of bacteria in your system. Dirty systems that we think that, okay, so far we haven't had any problem, so we are not going to have any problem from now on, they are in danger, definitely. If I was a manager who would think that, okay, so far I haven't had any case of microbial corrosion, so it is not likely to have any in the future, your facility will be in danger sooner or later. Okay, so there are issues as such that I have discussed in my books in details. I'm not going to take your time with those. However, these are the points that we have to be very careful about.
Thank you, Dr. Reza. Pasina, over to you. You mute.
Thank you, Dr. Reza.
Yes, you're welcome.
Maybe one last technical question to Pak Martin. I think as mentioned earlier by Pak Richard, I think they have concerns. Maybe Pak Reza also, Dr. Reza could have also. They have like the issue probably like in the tanks with the MIC. Maybe you could elaborate more if there's any effective NDT method, maybe like UT, corrosion mapping, or image scan and acoustic emission that could be utilized to prevent the premature MIC in the tanks, Pak Martin.
Okay, thank you, Pak Sina. Basically, this one is very tricky questions, yeah, and difficult to answer. But in my opinion, in almost all cases, MIC produce localized corrosion. So in my opinion, any NDT techniques can detect localized corrosion is applicable, such as UT or corrosion mapping, etc. But please be note that a major drawback to all monitoring technique is that one only monitors in the location of the probes or the accessible areas offered inspection. This thing will not be the areas that are colonized by the destructive microorganisms. So please consider that things. I think that's answer from my side.
Yes,
Thank you.
yes. I want to add to Dr. Martin's points. I agree, but don't forget that, NDT methods, they are basically used based on the assumption that pitting, for example, is the same. If it is coming from MIC, if it is from, I don't know, atmospheric corrosion, etc., etc. Morphology of the failure, unfortunately, morphology of the failure in MIC cases is not that different from abiotic cases. Therefore, I mean, yes, during 1980s, they were thinking that some people were thinking that the shape of pitting, for example, could be indicative of, for example, the case being microbial or not. This is something that nobody believes in today, okay? So the only technique that at the moment we have is to, as I said, monitor the bacterial population, also be aware that all these methods have their own pros and cons. Unfortunately, UT or radiography, etc., they cannot address any kind of, difference. At the moment, I'm authoring a book that I call as MIC Atlas. In that, I'm gathering a lot of cases of MIC and MID from both industry and academia. There you can see that the crack on, for example, observed on a piece of stainless steel that has been identified to be related to microbial corrosion is no different from the crack that, for example, has been observed on stainless steel exposed to abiotic cases. This is something that makes life very difficult and confusing for us. If you are a corrosion engineer, this does not mean that you are an MIC expert. If you are a microbiologist, this does not mean that you are an MIC expert. You have to be both, and this amphibian life is something that has to involve experience from material science, chemical engineering, electrical engineering, like, for example, electrical engineering, cathodic protection. Some people say that if, for example, in pipelines, you apply a potential of minus 950 millivolts versus copper sulfate, then it is highly likely that your pipe will be immune to SRB. No proof. No proof. We have cases where the applied voltage was even more negative than 1000 millivolt. Still, not only SRB did not die, they even become more active. So it is not a clear-cut story, When it comes to CUI, corrosion under insulation, almost everybody knows about it. When it comes to atmospheric corrosion, almost everybody knows about it. When it comes to, I don't know, acid corrosion, everybody knows about it. But when it comes to microbial corrosion, because you're dealing with living organisms which are much smarter than we are. You can never be sure. You remember in the definition of MIC, I said that under certain circumstances, they can even inhibit corrosion. Iron reducing bacteria, I have tested it. Under certain circumstances, iron reducing bacteria can even protect metal from corrosion. Here you are. So it is complicated. The more we learn, the more we understand that we don't know anything. And it has always amused me that some people, especially when you search YouTube, you see that some people, self-claimed MIC experts, they come and show you this. This is the case of MIC in our heat exchanger, which is not. Simply, it is not. How do you know? That's why I mentioned always start with skepticism. Always ask your question, what if it is not MIC? In one case I had several years ago, the operators of a pipeline were very worried about the failure they got in their in a pipe that had two types of corrosion products, black in color and brownish in color, okay? And because the pipe, the water, had a neutral pH, temperature was ambient, and they had a history of Pseudomonas bacteria, as soon as they saw this failure, they called for me. They said that, we have a case of microbial corrosion. Let's call Reza. I went to the site, okay? And then I said that, my friends, I have to do the test myself, okay? I untied my tie and I put on PPP, entered into the pipe myself, took samples, black sample. They were saying that it is iron sulfide and it is SRB. I took the sample and applied a few drops of hydrochloric acid on it. If it was iron sulfide, you would have smelled H2S. Nothing. Nothing. It was not iron sulfide. So I took it to the laboratory, dried it, and then applied magnet. Okay? And it stuck to the magnet. It was magnetite. Fe3O4. And the other layer was hematite. This shows that the oxygen scavenger had been administered unwisely. You had added it sometimes too much so that the environment had become deoxygenated. You got magnetite, and sometimes very less oxygen scavenger had been added so that you get a lot of oxygen and hematite. So it is not always the case that microbial corrosion may come and strike. And Pseudomonas is not such a surprise. If, for example, may God forbid, you have problem with some of your organs, like, for example, wounds, etc., Pseudomonas are there. So it is not that when you see a bacteria, you get panicked. On the other hand, it is not that you see bacteria and then you say, so far we haven't had any problem, so this time we are not going to have a problem. Both extremes are wrong. Thank you.
Thank you, Dr. Reza. First of all, the time is up, but we still have another question. Is it okay to continue to the last question, maybe? How how Dr. Reza and Dr. Martin? Is it okay if we continue the last question?
Yes, okay.
At your service, yeah.
Maybe only two, 3 minutes. Okay. So, thank you, Dr. Reza, for the explanation. Maybe there are a lot of people want to be expert like you, Dr. Reza and Dr. Martin. And what is your favorite resource or literature, online book about MIC that you would like to share with our listener? Okay, maybe from Dr. Martin.
Yes, I have several Dr. Reza's book. It is very good for reference, of course, and also for from other scientists. There are also plenty like from the BJ Little, H.C. Fleming, Videla, etc. If you want, I can share it.
Yes. Thank you very much. Unfortunately, I can only recommend my own books. Because basically the thing is that not because I have also those books. No, there is no.
No, they are good. They are good books indeed.
Thank you very much.
Sorry.
Very kind of
Yeah.
you. No, I'm not saying this because I am the author or main author of those books. It is because I have always, during my years in industry and both academia, I have always tried to blend academic curiosity with industrial awareness. Because if someone, I have always put myself into the shoe of an engineer who is in the middle of nowhere, has a problem regarding corrosion or microbial corrosion, and wants a quick, access, which is also reliable, and he just doesn't have time, or he's not in the mood of reading a lot of academic papers, etc., etc. He just wants to open a book, find the solution, and if the solution didn't work, he would say that it was Reza's fault. Okay. So this is the philosophy behind writing those books, or my LinkedIn notes or whatever.
I read some of your literature, and I think it's quite pragmatic for busy and hectic people like owner of a facility.
Thank you very much. It's very kind of you, and I'm glad that professionals like you appreciate it. This is something that when you come to my age, this will give you a very good effect on your power, and this will make you do even harder whatever you are doing. Thank you.
I think
Okay.
that's the legacy thing is very important for us.
Thank you.
You already have a legacy.
You're welcome. Thank you very much for your kind words. Thank you.
Okay. What a very interesting discussion today. And today I learned a lot of new things from Dr. Reza and Dr. Martin. Thank you so much. And also thank you for your time. And I hope our communication doesn't stop in here and we can meet in the future. And wish you all the best for your future endeavors.
Thank you very much. I also thank you all for organizing this virtual meeting. I really hope that I will have the opportunity of visiting Indonesia again and seeing my friends there. Thank you again for your time, and I hope to hear from you guys